remember, is a little Saturday. So. This clock is way off. Well, good morning. That's the last problem from yesterday. We almost finished it. So let's refresh our knowledge. Well, to solve this problem, first of all, we have to want to do that. Everything else comes after. And we need to figure out what kind of an optical device is being used. By now, we actually have learned about mirrors of two types, lenses of two types, a double slit, a single slit, a diffraction grating. And for each device, of course, we will have to use different set of equations. But in physics, everything begins from a picture. So the name of a device must be related to the interference pattern we observe on the screen, because for different devices, a different pattern. So we have a device here. If you want to do something more about it, you can draw something larger, like a line. All right, that's an object. Here we have a screen. And on the screen, no matter what device is being used, right across the device, we always have a maximum of intensity of light. That's the size of this maximum depends for double slit interference pattern and for diffraction grating interference pattern. That's a relatively small spot, fringe line. For a single slit interference pattern, it should be wide, large. And for diffraction grating, we need to know the pattern looks like this. 2 or 3 or 4 more maxima on each side, but with a huge dark space in the middle between those spots, fringes, lines. Which means, if we look at the pattern, this is the maximum, this is the maximum, this is the maximum. Do we see any minima? No. No. Because to see a minimum, we'd have to see a very narrow place with no light, dark, narrow. That's not the case, which means we cannot use the condition which could describe a minimum. That's it. So we finished calculating the distance from a second to the first maximum. These are the patterns, and it has to be imprinted in our memory until next Friday. And these are the equations related to each pattern. That's why we need to know the patterns, so we could relate pattern equations, pattern equations. And single slit, we have an equation which looks like an equation for a maximum intensity, but actually describes allocation of a minimum dark fringes. For a double slit or a double source experiment, if we could make two ideal light sources identical to each other, we could use any equation for the maximum, for the minimum, but for diffraction grating, we have to use only one equation for each maximum. And when we say a maximum, we mean at that location a constructive interference is happening between all light waves approaching that spot. And when we say a minimum, it means a completely destructive interference is happening at that location. So that's why all light waves cancel each other. There is no light at that point. Magic. So these are two actual patterns. This one you should recognize by now. The one on the left is a single slit, double slit, or diffraction grating interference pattern. Anybody? I cannot see you, so if you change your voice, you can say anything at all. So this one on the left. Single slit, double slit, or grating. Double slit, many bright fringes separated by many narrow dark fringes. Single slit is on the right. A wide central maximum, and then a minimum, another minimum. And if we want to see a pattern for diffraction grating, we need a diffraction grating. Where is it? Well, there's several, big, small. This one, it looks like a piece of glass, but it has many rulers, scratchers in it. And if I take a laser, that's the central maximum. Well, I want to cover mouse on my back. So this is the central maximum, but if I insert grating, we can see how many maxima. Now on the screen, well, one is over there, so the angle might be very large. But what is the maximum possible angle? 90. Now, let's see if I can show us that. This is vertical. Well, I can make it horizontal, of course. Just turn it around. But I want to have it vertical. Where's my stand? Very bright. So this is the beam, but what else do we see? Well, that's the beam. But we can see here, there's one more, which goes all the way up. And of course there's similar, which goes down, hits the table. So, and there is no light in between. Just doesn't exist, because right here where the diffraction grating is affecting the light, according to Huygens Fresnel principle. All those waves start interfering, and as the result of that interference, only certain directions survive. It doesn't have to be a transparent medium. We can make a mirror with many slits. That also would have been diffraction grating. And here, instead of a mirror, I just have a CD. Let's see. Here, when it reflects, it also creates extra maxima. Central, one single, many. But this is old CD. If I try a DVD, the spacing is different because we can fit more information on a DVD because the spacing between those grooves is much smaller. And if you use a Blu-ray, that will be even more effective diffraction grating. Now, I'm going to show you so you would know how does it look like. This is what I used. Nowadays, it's a very simple experiment. You just need a laser and a wheel with many possible slits. Well, I cannot plug it in right now. It aims at you. But if I turn it, that's it. So a laser, green laser, could have been red, and a wheel with slits. This is a multiple slit, so double slit, or you can play with a triple, quadruple slit. And this is a single slit with different width. And if we try to, which one? This one. If we try to change, yep. Pattern, small, bright, well, small relative to the original size. If I move away from the screen, of course we know the size increases, but if I now change the width of the slit, make it wider or narrower, so I can change the pattern. And Monday and Tuesday, you're going to be doing a lab very similar to this, but with additional equipment, which will allow you to actually measure the distance between, well, a couple of maxima, a couple of minima, and calculate the wavelength. That's how a wavelength of light has been measured more than 100 years ago. Well, it was much harder to do those days because they didn't have lasers. I'll be back. Now you have to think about how to calculate how many maxima can you see on the pattern created by any of the devices. The strategy is the same for all devices. Doesn't matter if it's a single slit or double slit or diffraction grating. The strategy has to be the same. So pictures. We have solved this problem, calculated the distance between the first and second maximum, but we didn't finish the calculation about the number of maxima. So the idea is simple. If we look at the screen, doesn't matter what device is being used, there's always a ray traveling toward the middle point, then one more, and one more, etc., etc. So for every next number of m, angle increases, but that angle, of course, cannot go above 90 degrees because above 90, light would travel away from the screen. That's it. So 90 is theoretical maximum. Theoretical. Of course, in order to reach the screen somewhere, assuming it's infinitely long, the angle should be slightly less than 90. That's it. So the condition for the mth maximum is this. And if the angle has to be less than 90, that means the sine of this angle should be less than 1. And that means this ratio should be less than 1 because it is equal to the sine of any angle. But what we are solving for m, so I don't remember, 8th grade, inequalities, m should be equal to this ratio, or less than this ratio, equal. Technically could have been. So m that is correct, and that is correct, and in this particular case, our numbers are, that was 10 to the negative 6th in meters, and that is 480 in meters. So please take a calculator and calculate this ratio. It has to be some number. And please just tell me that number. Is it a whole number? If you calculate this exactly, this ratio exactly, what do we get? Yeah, so why have you been waiting? 2.08, that's the exact, but what do we know about number m? What does it do? It counts things. 1, 2, 3, 4, 5, 6, 7. Can it be 2.08 or 2.75 or 3.16? No, it can't. These numbers only have to be whole numbers, integers. So that tells us that the maximum value, cannot fit it here, m maximum should be equal to just 2. It cannot be 3. It only can be less than this. And now, what does it say? Well, it says that actually my picture is almost done. We have central or 0th maximum, then first, then second, but we also should have first on another side, second on another side, and that's it. That's done. So 1, 2, 3, 4, 5, together we would see just 5 maxima produced by this diffraction grating. That's it. How many? 5. Any questions? Well, I'm not sure if this is better readable, but I tried. Now, question to you. What's going to happen if we use simultaneously with the same diffraction grating 2 or maybe more different colors? So in this situation, I have a laser pointer which produces green and red, so I can press two buttons at the same time. And use the same diffraction grating and look at the pattern, and what should I see? The equation which relates all the variables is on the screen. You just need to kind of use it. That's a very rare situation when we may require using a little bit of thinking. We should look at which maximum. What about the central? For the central maximum, m equals 0, so any wavelength can be used, still the angle is 0. So we have to look at the next maximum, which is first, for m equals 1 and the same grating, how does wavelength affect the angle? That's it. If the angle increases, to increase the angle, what should we do with the? Okay. That's green. That's red. That's both. That's the central maximum. Of course, central maximum is not affected, but we can see that the first, for the green, is closer because it has a shorter wavelength. And when we're increasing wavelength, we're increasing the angle. And by the way, this is another way how we can make a rainbow. Doesn't have to use a prism. We can use a diffraction grating. It splits light, but it splits light in the opposite way, actually. Now the red is bent more than the blue. Well, this is basically related again to how light interferes. And in this situation, because the blue color has a higher frequency, it's affected less than the red one, which has a lower frequency. And the answer is, well, we have to do it. This is what we can write. When wavelength goes up, the angle goes up. That's it. That's the answer. Well, we are done with the slits. Covered everything. Now, we have to step back for the moment in order to go forward in the future. We've talked about standing wave formation. And we know what should happen. But how? Well, we know that when one source generates a wave and then a second source generates a wave in the same space, they overlap, they interfere, and they produce interference pattern. But we never answered the question, where exactly we will see a maximum or a minimum. We just know they are there. Of course, there's a straightforward mathematical approach. For example, we can write a wave equation for first wave, for the second wave. They meet somewhere, interfere, and we can do trigonometry to add cosines or sines. But of course, there has to be a better way. And of course, it begins from a picture. So please, enter your answer for this question. I need what I need. I need This is what I need. This is what I need. Recently I found in this drawer a picture which I made exactly a year ago. No one wants it, so I'm going to just put it back. I cannot trust it because I just don't trust it. Just don't. Now, so what is wrong with this picture? There is a definite answer to this question. So what do we have to do? We have to draw a bigger picture. We always have to keep in mind a bigger picture. So first we need to figure out a better representation of a wave. And well, this is how a wave looks like. But if we try to draw it, that's not going to work for us. So we use a color coding. For every wave, there's a crest and a trough, a crest and a trough. So we can imagine that we are looking at this wave straight down or like this. In that case, we don't see a wave. We only see a location of a crest, trough, like here. This is the same wave, well, kind of. And each line represents crest, trough. What is black? The equilibrium location, the equilibrium waves about it. And now we can imagine how it's traveling. We just need a source. I don't know what you see. This is okay, a source. And a wave is traveling from this source in all directions, everywhere. For example, here, what's going to happen? Well, here, the red means right now it's up, crest, equilibrium, oops, trough, equilibrium, crest, equilibrium, trough, equilibrium. That's how it oscillates up and down, up and down, up and down, everywhere. Now we can add a second wave. They're supposed to be identical, more or less. And what we see is two waves traveling, well, in all directions. When they overlap, what can happen? Anything. If they overlap, like say red and red, that means crest and crest. That represents the maximum intensity. If they overlap, let's say blue and blue, trough and trough, another maximum intensity. What does black and black mean? Nothing. It just momentarily, it might change. But what does red and blue mean? Crest and trough, destructive interference, they cancel each other, the minimum of intensity. But before doing all this in space, the easiest way is just again take a look at what we know already. Between two sources, there has to be a standing wave with the maximum right in the middle. We know that. That's not a new information. That is not a new information. That's how it should look like, well, more or less, maximum. Then, a minimum as a result of two waves. Well, okay, maximum, minimum, and where's my blue? Again, maximum. So we can, this is the central maximum. This will be the maximum number one. It's all when they add it up together, it's blue and blue, it's a maximum. And another maximum, number 1. This will be maximum number 2. And now you can see it. This will be the minimum, number 1. The 0th minimum doesn't exist. We count them from 1. Now, we know that from the past because we used a different method. So we know it has to be the maximum, and then we know for the standing wave, a quarter of wavelength away should be minimum, a quarter more, another maximum, a quarter more, another minimum. That's what we know. But now we need a more general description of this phenomenon. We know it because waves travel from sources and overlap. So this is what we can start thinking about. This is the distance traveled from the first source to the central maximum. This is the distance traveled from the second source. Of course, for the middle point, they are equal to each other, which means the difference is equal to 0. There is no difference. And that's why they are always in phase. However, now we can make a very important step forward. The same condition will work for any point on this line, which is perpendicular. I can take any line, any point on this line, pick any point P, and the waves traveling from both sources to the sources to this point will travel exactly the same distance, will be always in phase, will always produce the maximum, which we call central. So if I place a screen here and look at it, I will see the bright spot. What about this one? The minimum, maximum. This is the maximum, blue one. The maximum, the next maximum, number 1. Well, for this guy, this is distance traveled from the first source, the new L1. And this is distance traveled from the second source, the new L2. Now, they are different. But if I calculate this difference, well, this difference has a name, path length difference. This is the path of the first wave, and this is the length of this path. This is the path of the second wave, and this is the length of this path. And path length difference, which is defined as magnitude. And again, different textbooks define it differently. I define it as magnitude of the difference. Will be equal to, in this situation, longer path minus shorter. What is it equal to? The easiest way to figure it out, to use the symmetry. Yeah. There is exactly the same distance on another side, and it should go from that source to this spot, which is symmetrical to this one. We can just imagine that this is what we're doing. Yeah? That's a line of symmetry. Exactly same distance. Here. This is the new L1. Now we can see the difference. The difference literally is difference between this arrow and this arrow. This is the difference. This is the path length difference for the first, not for the zeros, for the first maximum. So what do we see? Blue, black, red, black, blue. Every distance from blue to black, or from black to red, or from red to black, or from black to blue is equal to exactly the same number, which is what? Anybody? Cannot hear you. No. Where is the lambda here? This. Red to black. Lambda, half, quarter. From red to black, this is the black. A quarter from black to blue. A quarter from blue to black. A quarter from black to red. A quarter. So a quarter, a quarter, a quarter, a quarter. How many quarters? 4. 4 quarters. So that is literally what it is. 4 quarters, which means 1 wavelength. Why? I can see everything. What cannot? This? I cannot hear you. If I cannot hear you, I cannot. What? You people, I cannot hear you. You have to speak loud. Well, I know that. I know that I'm not transparent. This is something I can't fix. So you have to wait or act. What if you act? You have to be louder. That's it. It's very simple. So for the first maximum, no. No. Write a complaint to the designers of this room. They should have put a second projector with a side screen. Now, for the first maximum, the path length difference is equal to this. How many more points do we have with the same condition? More. There is a line for many, many points when difference between distance traveled from first source and distance traveled from second source, difference will be the same. Where is that line? Well, now you don't see it. Now you see. This is the line. For any point on this line, if I calculate the path length difference, path length difference will be equal to exactly 1 wavelength, which means for any point on this line, I will see a maximum intensity. And now, if I place a screen right here, that will be maximum, the central maximum, and that will be maximum with m equals 1. And we can repeat exactly the same reasoning for all other points for more lines. But let's do one minimum. The first minimum right here. So, for this minimum, this line represents the length of the path number 1. This line represents the length of the path number 2. Now to calculate the path length difference for the minimum number 1, we have to subtract 2 numbers. This minus this equals what? Well, now we can do the same thing. Oops. There's exactly the same minimum on another side. Again, with the same number, 1. So this line has the length of 1, L1, L1, L2, L1, And I don't know, I should have brought more markers. Anyway, from here to here, we should see the path length difference from black to next black. And that is what? Equal to what? I can see you moving your lips, but I cannot hear. A half. That is a half of a wavelength. A half, 2/4, a half of a wavelength. So there is, of course, more. There are more points like that which lie on this line, and for each line, like for each point on this line, if we calculate path length difference, it will be equal to a half of a wavelength, which means that's going to be a minimum here. And we have lines in on another side. And for each next maximum or minimum, we can repeat exactly the same calculations. And the result is to have a maximum path length difference should be equal to some natural whole number of lambda. And to have a minimum, this path length difference should be equal to some odd number of halves of the wavelength. The first odd number is 1. The next odd number is 3. So these are 1, 3, 5, very similar to standing waves in a pipe with one end closed, one end open. Even numbers don't work for minima. And that's it. Now we know what path length difference is, what it means, and how it has to be calculated if we need to. And now I'm going to put it in a drawer for 1 more year. Well, this will be the photograph. So I've put some slides which kind of say what I just said, but it was kind of messy. So this is just a reminder of what we just did. We started from the standing wave between the sources, and then we started looking at what it should be happening in space. We used red, blue, and black color to represent different parts of a wave. And then we do calculation of the path length difference for different maxima or different minima. And it turns out for each maximum, the path length difference should be equal to a natural whole number of wavelengths, and for minimum, odd number of halves. And that's how a standing wave is being formed. And we saw, and I can show you again, just in case, we saw an applet which might be helpful to visualize what is happening. These are, well, first of all, of course, you can just look at a traveling wave generated by each source individually. This is a traveling wave. This is a traveling wave. But when they overlap, we get a standing wave. And right here, again, here, there is no wave at all. But here, wave oscillates. If we look at this blue, black, red, black, what does it mean? It oscillates in time, but it oscillates here with maximum possible amplitude. That's what this word maximum means. maximum amplitude, maximum intensity, maximum energy. And for maximum or minimum, path length difference should be equal to natural number of wavelengths or odd number. So that's for the maximum, that's for the minimum. And here we also see different mathematical expressions for the same fact. What does odd mean? Well, odd means strange, but also it means if we take number 2 and multiply by any whole number and subtract 1, we always get odd number. So we can replace this word odd with this mathematical expression, but also we can multiply by a half, and that will give a different expression. All these expressions represented on the equation sheet. Which you want to use, it's up to you. It doesn't matter. They all are mathematically identical. They all represent the same fact. For the minimum, we have to count halves. Now, one more time, the same statement. For each maximum, path length difference should fit natural number of lambda. For each minimum. And this is the summary. And in this summary, I just want to point at several features. For example, for this number, many textbooks use different letter, N, M, K, doesn't matter. For path length difference, or for each individual path, people use different letters, doesn't matter. We can use any, or S. For an odd number, you can use combination with a plus or a minus. I prefer using a minus. And people even count these numbers differently. Well, for maximum, it starts from 0, but for the minimum, because zeroth minimum doesn't exist, I prefer start counting from 1, but different textbooks might use it differently. Now, we can hear, and that's how we can study the standing sound wave. For the light wave, we have to use a screen and to look at the screen. But there is also a big difference between sound waves and light waves. For the light waves, because the wavelength is tiny, all distances are huge, which means we can actually calculate path length difference. Let's say we have two sources, and because the screen is very, very far away, these rays are basically parallel to each other. We cannot see the difference. So when they reach the screen somewhere, the path length difference will be equal to this. This is how much longer the ray number 1 travels. And we can calculate this. This is path length difference for two rays. If distance between two slits or sources is d, and this angle theta, path length difference over d should be equal to the sine of this angle, or path length difference equals this. And that is how we have arrived to the expressions we've been using already for each maximum or each minimum. Because on one hand, path length difference always have to be equal to this for a maximum. But on another hand, for light, it also is equal to this. So we just make this is equal to that. That's it. For each maximum to be seen on the screen, this product, d times sine theta, should be equal to m times lambda. And for a minimum, the same reason. Again, this expression works for any wave, sound, light, mechanical, doesn't matter. But for light specifically, we can add one more expression. And now because this has to be equal to that, this becomes equal to this. And that's how we get our standard expression for the minimum. The summary, some history. Again, the notion that light is a wave didn't take physics by fire. No, it took almost 20 years for people to actually switch their mind from thinking of light as particles to thinking of light as wave. And it happened in France mainly at first. Oops, wrong. When French Academy was kind of having talks about it. I need this again. Don't be scared. So right here, it's a classical experiment. A beam of light encounters a tiny obstacle, a ball. According to the classical theory, of course, a ball has to form a shadow. Nothing should be seen behind it. Shadow. But the wave theory of light predicted that in the middle of that shadow, there should be light because it bends and interferes. And well, at that time, it actually was able to check, and they did, and there is a light in the middle of the shadow. And that proved the fact that light actually does have wave properties. And after that, very quickly, everyone switched from particle theory of light. They betrayed Newton. To the wave theory of light. And they had to also explain, using the wave theory of light, the formation of shadows and the dispersion, and they, of course, succeeded, especially after Maxwell's equations being written. So this is what just I said. Particles can't do that, just can't. So we have to make a conclusion. Light, kind of, no particles. Now we're done with the slits and path length difference. Now we are moving on to the next stage in the study of interference. This is a special case, so-called thin film interference. Well, what is it about? It's about properties of light in the medium. So please tell me what you think. In the medium, this is a situation when I strongly hope for the completely correct set of answers, 100%, because we've talked about it later, before, we've talked about it before, probably 3 times already. It's about frequency and a wavelength and a speed of a wave in a medium. That is question number 5. 100%, 100%. No. It's a sad day. So, frequency is not a property of wave per se. It's a property which provides to the wave by the source. So we know speed changes, and we know, so basically, these are choices you had to make. But because frequency is the property of the source, the frequency stays the same. But if the frequency stays the same, that means other variables have to change. So when light travels, let's say from air and water, doesn't really matter, because, well, in the air, speed equals frequency times wavelength. And in water, the new speed will be equal to the same frequency times wavelength in water. Speed over speed, frequency times wavelength over frequency times wavelength. This ratio is equal to what? By definition, speed in the vacuum over speed in the medium is equal to the index of refraction of that medium. And frequency, because the same, getting cancelled. So the wavelength in water will be equal to wavelength in air, same as in vacuum, divided by the index of refraction. We knew that, we didn't use that. So this is not a new fact, we just didn't use it, but now we will have to use it. So the summary, again, we saw this slide, the same slide, slightly differently. Now we have to talk about thin film interference. What is it? Well, let's say we have two pieces of glass. 1, 2, and in between we put some, I don't know, oil, something transparent, but very thin, which means the thickness of this medium is much, much less than the size of any piece above or below. And that means everything is happening here. So we don't really care about the presence or absence of those boundaries. All we care about is this. There are two boundaries. This is what we call film, because it's thin, might be micro, maybe even nanometers. And we have two media, one is above it, one is below it. And the medium is described by the index of refraction. This is also called the index of refraction in a film. That's it. What is happening now? Well, there are many possible situations, but we only consider one specific case. First, light travels straight down, perpendicularly to all surfaces. So what's happening here? Well, technically it could be partially reflected, partially transmitted, partially reflected, partially transmitted. And we're also looking straight down, so observe what is happening. And right here, this reflected ray and this reflected ray interfere, and something might happen. We don't know what, that's our goal. The problem is that we don't really see anything because everything is overlapping. That is why, instead of making a picture of what exactly happening, we make a picture which tells us what should be happening. So the incident ray, which is partially reflected, partially transmitted. We just ignore anything traveling down because our eye is assumed to be above. This light ray also getting partially reflected. And of course it might be partially reflected again. We ignore that. There is another ray which is transmitted, and these two rays now will interfere. Two waves overlapping, they must interfere. What can happen? This word maximum means a constructive interference may happen. What does it physically mean? It means this light will be seen bright for the person looking down. Minimum, this word means a destructive interference happens. What does it mean physically? It means there actually no reflection. The light of that color, that wavelength, will be traveling straight through. It doesn't go back to the observer. This is how anti-reflecting coating works. You can use the film with a fixed known thickness and the index of refraction in order to make certain light not reflected, completely transmitted. Or vice versa, you can make it completely reflected. And that's how it's been used. Now, of course, we need to figure out how to describe it mathematically. Well, this is the ray number 1. This is the ray number 2. For the maximum, path length difference should be equal to something. For the minimum, path length difference should be equal to something. So it is all about path length difference. That's why we had to do it. Well, there is, again, a nice applet which you can play with, which shows what's technically supposed to be happening at exactly the same location, but in order to us to see it, the author spaced all those rays. So this is the original incident ray. Here, the first reflection happens. Here, the second reflection happens, and here we can observe interference. In this particular case, actually, what we see is a destructive interference. Those two waves are out of phase, but depending on wavelength or index of refraction, we can see different situations. So this is what thin film interference is about. Light travels down, first reflection happens, second reflection happens, interference happens. And this is a very important statement. It's a thin film interference. Everything is happening in the film, which means for all our calculations, we have to use the wavelength in the film, in the second medium. This is when we should observe a maximum of reflected light or no reflected light at all. This is how much longer the second ray travels. It travels this distance down, and then it travels this distance up. So thickness T plus thickness T tells us the geometrical path length difference. But the reflection is happening, and the question is, does reflection matter? Yes, it does. We have a mechanical model which tells us what might happen depending on the end. So, start. A wave travels approaching the wall and gets reflected and travels back. See? This is a situation similar to a pipe with one end, well, at least one end open. This is an open end. But what's going to happen if we fix the end? Now this wave is pushes on the wall or on the fixture, and the wall pushes back. And in the result, the reflected wave flips. So reflection matters. Reflection might affect or not affect the wave. In our situation, it's not a wave and a wall. It's two different media, like this one. It's like two ropes. The first rope is thin, light, and the second is thick, heavy. And in that case, it pushes back, and the reflected wave flips. And this is a situation similar to air and water reflection. Air has low index of refraction 1, water high 1.3. What is happening if it's a water-air situation? Heavy rope, it's too heavy, so it just gets through, and when it reflects, there is no flipping. That's it. And we have to remember that. Sometimes wave flips, sometimes wave doesn't flip. And flip means it, well, physically, if you have a graph of a wave, you have to flip it. But mathematically, it is also identical to have the same graph and shift it in any direction by exactly half of a wavelength. You take this graph, you flip it, you get from a crested row. You take the same graph and you shift it by half of a wavelength, you get again from a crested row. So flipping is identical to extra distance. That extra distance should be taken into the account for the path length difference. That's it. That's what we need to remember. When light travels from one medium into another, and if the top medium has index of refraction higher than the bottom, like water, air, this is this one. There is no phase shift, there is no flipping. We don't have to add any additional distance to the actual path length difference. But in other situation, when it's air and water, low, high index of refraction, thin, thick rope, it flips, and we have to add additional half a wavelength to the actual path length difference. So we have to use not the geometrical path length difference, but physical effective, E stands for effective path length difference, which may be the same as geometric, or may be different by half of a wavelength in the film, because everything is happening in the film. That's it. That's the physics of it. That's only new information for this phenomenon we need to know. That's the only new information. So the summary, the effective path length difference should include two terms: the actual physical geometrical, distance down, distance up, plus, if it happens, an additional half of a wavelength. That's it. And now, if that effective path length difference turns out to be equal to odd number of halves of a wavelength, those waves cancel each other out. We observe completely destructive interference. This light actually not getting reflected at all. But if, so we don't see it, that's what it means. But if we look from above, but, if effective path length difference turns out to be equal to this natural number of wavelength, in that case, we will observe reflected light of this particular color. That's it. which means now theoretically you can solve all the problems related to thin film interference, all of them. Yes?
One of, like, you know, there's two reflected light rays, right? Can one of them be flipping and the second not flipping? Or like, can all of the equations happen? Because
In order to solve a specific problem on thin film interference, we have to use the 5-step approach. Step 1. You look at the boundary number 1 and you make a choice. Does wave flip or not? And it does if index number 2 is higher, and it doesn't if it's lower. Step number 2. You move on to the second boundary and you make a choice again. Does it flip or not? Because it may or may not. That depends, and again, which index is higher, which index is lower. Now you have 2. What do you do now? This. And in different textbooks, people calculate effective path length difference differently. I use magnitudes. I use absolute value. That makes things easier. Some people just use regular parentheses. So what do you see here is the actual effective path length difference. It is always equal to the actual physical geometrical plus. And now what's happening here? Well, if there's only one flip, that will be equal to a half of a wavelength. A half plus or minus 0. If it will be 2 flips, they cancel each other. If it will be no flips at all, this is just 0. That's it. So in general, effective path length difference may be equal to 2t or 2t plus a half of a wavelength. That's only can happen. Yes?
and there the delta T and delta B is like, one is for the first.
T means top, B means bottom, or first and the second, yes. Delta T, I think it was here, yeah. Top surface, delta T. B, bottom surface. And now we use both. So again, the path length difference will be different from effective path length difference only when one flip happens. It might happen here or here, but if it happens here and not here, you have to add a half of a wavelength. If it doesn't happen here but happens here, it will be a half of a wavelength. But if it happens here and there, in that case, they cancel each other out. It's like not happening at all. Step 4, depending on the situation, we have to set effective path length difference to a specific condition. If we see reflected light, it's maximum. If it's canceled, it's a minimum. And step number 5, of course, solve it mathematically. Now, there's a little bit tricky part here. We don't see like central maximum, first, third. We don't see those. Plus, flipping might affect the phenomenon. Plus, it doesn't have to be just one specific thickness, maybe different type, more and more, which would lead to the same result. So this number m in this phenomenon technically may start from any number, from 1, from 0, even from 2 sometimes. How do we define it? This is how. The effective, in my approach, the effective path length difference cannot be negative. So we can try different m's. If m equals 1 would give a negative number, it's a wrong number, and we have to move to next. Try m equals 2. There is always the first value for m which gives first possible, well, solution. Well, we're going to do examples, of course, right now. So this is a standard experiment. I'm going to do it right now. But before, I want to ask you a question. What do you think? This is not a physics question. It's not related to mathematics. This is a short memory question. That's why, technically, it's not really important, but it gives me time to set up my experiment. So all I need is just soap. I don't see if I see anything. Okay. I felt it. Let's see if I had too much light. Maybe. Well, not very bright, but you can see horizontal colored fringes. Red, blue, oh, it pops. What if I kill the light? This bulb is dying. It's Friday. Doesn't really help. Well, one more time, I will switch back. Yeah, a little bit red, a little bit blue. So what is happening here is a thin film interference. And what we have is a thin film of, well, basically water, of course. Between what? Air and air. So we always have to name each medium involved in the experiment. In this situation, it's air, water, air again. So this thin film, because of the gravity pulls down, is thicker at the bottom, thinner at the top. So it is a wedge. And for this wedge, this is air, water, air. First reflection happening here, air-water case. Second reflection is happening here, water-air case. So index low, index high, then index high, index low. And high index for us, like a mnemonic rule, means heavy rope. And low index, small number, means thin, light rope. And what do we say? Here. Well, N1, N2, N3. N1 is 1, N3 is 1, N2 is 1.3. So here it's like a light rope, heavy rope, it should flip. So there is a phase shift, an equivalent of a half of a wavelength of extra path. But here, it's like a heavy rope. To the light, there is nothing, no shift, no flip, 0. But now, of course, we have answered the most important question, how to change the actual geometric path length difference to write the physical effective path length difference. We know what to do. So 5-step method says, again, the picture, oops, wrong direction. Again, the picture. First ray, second ray. For the delta top, we should write a half of a wavelength. Where? In the film. Don't forget that. Everything is happening in the film. Here, for the reflection at the bottom, we should write 0. The thickness of the film, well, standard letter is T, is basically distance between the point where first reflection happens and the point where the second reflection happens. In this situation, the thickness depends on the location, but some problems use a film with the same thickness, so different problems. And what is happening, because of constructive interference at different thicknesses, we can see different color is amplified, and we can see green, blue, pink, because it depends on the wavelength. Now, we need to write an expression for effective path length difference. So people use just delta, or E path length difference, or delta R effective, wherever it is. It has to be equal to actual geometrical difference, T plus T, plus, in our situation, it's this. So we have to add a half of a wavelength to the actual path length difference. Now we have to set it, that's step 4, set it to a right condition. So for that we have to read carefully, because that might be tricky sometimes. Should we set it to a condition for a maximum of intensity or of a minimum? Here we have a clue, a hint. Constructive interference happening. So effective path length difference should be equal to this product, natural number of lambda. Where? In the film. Don't forget that. People keep forgetting that. So this is our equation we need to solve now. Should be equal to this plus this. What are we solving for? Thickness, T. You need to add an extra slide. M times this equals this plus this. Because we are solving for T, we have to solve it for T. M times this minus this divided by 2. As we can see, for the red light, (661) with the wavelength 661 nanometers. There are several solutions because m is not just a fixed number. Could have been, and we don't know yet, 0 or 1 or 2 or 3. So what do? We try them out. Let's say m equals 0. That gives thickness negative. That's wrong. It cannot be negative. It could be approaching 0 sometimes. And it is actually approaching 0 at the top. You know, all water being pulled down. So it's almost 0 thickness at the very top of this wedge. But definitely not negative. So m equals 0. Wrong. What do? We try next one. T equals 1 times wavelength minus a half of a wavelength divided by 2. So this gives me wavelength over 4. A good number, positive number. And that's the first value for the thickness which satisfies this condition. And will be the next. Now, technically, m equals 2, m equals 3 also is correct. That is why we see several lines with the red light. Red, again red, again red, again red. All we have to do now is just, oops, go back. Just plug the numbers, 661 over 4. My throat is sore. I have to drink it. I have to walk while drinking. It's your time. You have to say something. Yes?
It's not.
Hmm?
It's not.
If you insist, that doesn't make any difference. It means the answer will be nanometers. Yes? People pay attention. So I'm going to be happy the whole weekend now. 669 nanometers is the wavelength of the red light in the vacuum. No one ever says this explicitly, but you need to remember all these numbers related to vacuum or air. But this is not in a vacuum. This wavelength must be in the film. What do? We know the wavelength in the film equals wavelength in the vacuum divided by the index of refraction of the film. So we have to divide this number by 1.33. That's it. So we have the theory, we have the strategy, we have the solution. Done. Now, on your way out, which is going to happen very soon, I would recommend you to actually play with this. This is the wedge. You can see some rings. This is a wedge. You can see some colored shapes. And this is a filter, thin film filter, which cuts light of certain color depending on how you look at it. These are the pictures. That's it. Okay, so I'm going to do more examples on Monday. Thank you. Have a nice weekend. No lab today. That's very important.
Yes.
Yes.
If I was sent out an email about it, how if we got 0.25, once taken off for units, to talk with you about it. Yep. Should I email you, or do you want to just?